quite tectonic when it takes off. But it does fit on pad 39A, which NASA's been kind enough to allow us to use, where because they somewhat oversized the pad in doing Saturn V, and as a result, we can actually do a much larger vehicle on that same launch pad. And then in the future, we expect to add additional launch locations, probably adding one on the south coast of Texas. But this gives you a sense of the relative capability if you can read those. But yeah, these vehicles have very different purposes. This is really intended to carry huge numbers of people, ultimately millions of tons of cargo to Mars. So you really need something quite large in order to do that. So talk about some of the key elements of the interplanetary spaceship and rocket booster. We decided to start off the development with what we think are probably the two most difficult elements of the design. One is the Raptor engine, this is going to be the highest chamber pressure engine of any kind ever built, and probably the highest thrust to weight. It's a full-flow staged combustion engine, which maximizes the theoretical momentum that you can get out of a given source fuel and oxidizer. We subcool the oxygen and methane to densify it. So compared to when propellants are normally used, they're used close to their boiling point in most rockets. In our case, we actually load the propellants close to the freezing point, and that can result in a density improvement of up to around 10 to 12%, which makes an enormous difference in the actual results of the rocket. It also makes it gets rid of any cavitation risk for the turbopumps, and it makes it easier to feed a high-pressure turbopump if you have very cold propellant. Really, one of the keys here, though, is the vacuum version of Raptor having a 382-second ISP. This is really quite critical to the whole Mars mission. And we're confident we can get to that number, or at least within a few seconds of that number, ultimately maybe exceeding it slightly. So the rocket booster, in many ways, is really a scaled-up version of the Falcon 9 booster. You'll see a lot of similarities, such as the grid fins, obviously clustering a lot of engines at the base, and the big difference really being that the primary structure is an advanced form of carbon fiber as opposed to aluminum lithium, and that we use autogenous pressurization and we get rid of the helium and the nitrogen. So this uses 42 Raptor engines. It's a lot of engines, but we use 9 on a Falcon 9, and with Falcon Heavy, which should launch early next year, there's 27 engines on the base. So we've got pretty good experience with having a large number of engines. It also gives us redundancy, so that if some of the engines fail, you can still continue the mission and be fine. But the main job of the booster is to accelerate the spaceship to around 8,500 kilometers an hour. For those that are less familiar with orbital dynamics, really it's all about velocity and not about height. So really that's the job of the booster. The booster is like the javelin thrower. Sort of, it's got to toss that javelin, which is the spaceship. In the case of other planets, though, which have a gravity well which is not as deep, so Mars,